In this video, I want to explore the utility of integrating large language models into the JMP environment. So these data represent measures of fitness. Oxygen is a proxy for fitness levels. And the motivation of the study was to say, well, measuring oxygen is very expensive, measuring heart rate is very cheap. So can we basically predict oxygen or fitness levels based on these metrics? We also have some demographic information. Okay, so that's the principle here. And runtime is the subjects would run in a particular distance. How long did it take them to run a particular distance? This isn't a video about these data, but I'll give you some sort of context. What we're going to look at is this JMP assistant, which is based on what I'm calling the Nike framework. NIKE, navigation, interpretation, knowledge, and execution. I'm going to use a couple of data sets which show the power of this holistic approach of using all of these different components of the framework. But for these data, these fitness data, I want to focus on those individual pillars. So let's start off with navigation. So what do I mean? I really just mean, just give me basic navigation information for how to work with JMP. So how can I perform a one-way ANOVA? And optionally, I could say for oxy versus sex. So I literally just want to know which menu options to go to, because if I go to the Analyze menu, you don't see an option for testing for normality or one-way analysis of variance or whatever. So this is just going to help me know where to go. And you can do that using just ChatGPT or Copilot or the Learn bot that JMP have produced, but they would tend to give you quite a lot of reading. And the motivation of this is just to give you a 1 or 2 line instruction. So let's say, let's imagine I'm actually going to do it. We already have the analysis open. So this is the one way. So let's perform the analysis. So I've got the analysis open. And now I'm using the large language model to give me interpretation. So I could say something like interpret these results. So now I get a summary of some of the key statistics in here. And let's just see what it says. The p-value is less than the common threshold of 0.05, indicating a statistically significant difference in the means between the sexes. And so that's the final conclusion. And of course, we could have phrased this in different ways. I could have said, is the result statistically significant? And we get the answer. Yes, the result is statistically significant. And therefore, we conclude that there's a significant difference in the mean of the oxy levels between male and female subjects. That's interpretation. Let's think about knowledge. Well, knowledge might work at a couple of levels. It could be knowledge about statistics. Give me a definition of an R-squared statistic or the analysis of variance table. Or maybe knowledge about what we're seeing in JMP. So what are the green diamonds? And we get an explanation of the green diamonds. Now, one of the motivations for this design is to keep it as responsive as possible, because if we have to have if there's lots of latency, if we have to wait a lot of time to get answers, we're not going to ask questions. I want to be having a conversation. I want to be able to see things, do things, and interact in the same way. The other thing is, if it takes too long, if I'm asking it how to do something, I may as well just do it and go to the menu system and not bother with all this typing. Let's take another look at general knowledge. What assumptions are being made? And I also try and keep things quicker by reducing what I type, although it does risk the large language model not knowing what I'm talking about. But hopefully it knows what I'm talking about, and it gives me the assumptions for one-way ANOVA. So we've seen navigation, that's the N. Interpretation, that's the I. We've seen here knowledge, that's the K. Finally, we've got execution. So let's take a look at this third test here, homogeneity of variance. So let's test for homogeneity. I'm not going to try and do that. Test for equal variances. There we go. And hopefully it will run a test. It's done a test. And this is an interesting example. So a lot of what I'm showing you, I think, is interesting, impressive, but at what point does it become sort of compelling and actually beneficial and useful? And I think this is a good example of where it can be useful, because at this point, we're presented with 5 tests. What are the 5 tests? And which one should I use? Right? Perfectly sensible question to ask at this point of the workflow. So it gives me the tests, and I'm a bit disappointed with that answer, actually. So large language models are not totally repeatable in terms of what they do. It's not giving me as much information. Well, it's giving me what the tests are. So it's not giving me, maybe I should have said I should explain not what they are. I know what they are. I'll explain them. Explain the 5 tests. But we do also have this drop box here where it says default output. Does allow me to say, give me a more verbose output, or restrict it to a single sentence. So this is better. I've got an explanation of the different tests, as well as it shows that the associated p-values. And at the bottom it says, well, all 5 tests basically gave you the same conclusion, so it doesn't really matter. But for general use, the Levine's test is often recommended. So that's fair enough. It's kind of given me, okay, if I had to choose one, choose Levine. I'd say that's reasonable. People would probably say choose Levine or Brown Forsyth. I'm happy for it just to say Levine. So that's the execution. So let's take maybe some other examples here of working with all of this in combination. Let's model. Well, I could say, how do I model Oxy versus all other columns? This is really what we would do with this data set. And so we go to the Analyze menu, choose Fit Model, and then do these column assignments. One of the reasons it's called a Nike framework is because we can just do it. And so now I have my analysis here. Let's take a look at which model terms are significant. And it gives me the 3 terms. I could say build a new model using only these 3 terms. Like so. So those are some examples. And as we run a command, because we know the sort of platform that's been launched, we can kind of provide some sensible follow-up questions, interpret the R-squared statistics, summarize the results, which terms are significant, build a new model. So let's maybe do some other types of analysis. And for this, I'm going to switch to a different set of data. Well, let's me do one thing with these data. Correlate the heart rate columns. So this shows me the correlation between the heart rate columns. And notice the fact that it has to kind of take heart rate columns and work out, this is the real advantage. The disadvantage of large language models is we have to do typing. The advantage is we can use natural language, so we don't have to memorize commands. We can just type the way we are thinking, and it's also very tolerant to typos and so forth. Okay, let's switch to another data scenario. Here I have some process capability data. There's over 100 columns. What I could do is to well, actually, let's just do I was going to choose a subset. We could just do a subset. I could do process capability on the NPN cols. So it's kind of nice. You don't have to kind of pick the columns individually, and it will just pick out those. And you can see we've got 11 of those. But let's try and do something more challenging, where we'll see, hopefully, the real value that can come from a large language model. So I'm going to do process capability on all the cols. So here we are presented with lots of information. I'd argue we don't actually have lots of information. We are overwhelmed with data with these results. And we're going to use the large language model to compress this to a manageable size of actionable information. We can do things like report the worst performing variables or the best. That's all sensible. Or just summarize the results. I sort of want to summarize the results, but I want to guide it a little bit. I'm going to say summarize these results into 3 groups: capable, not capable, process shift, other. Okay, so there's another. So we're going to have 4 groups. I'm going to let it decide what the other one might be, if any, if required. Logically, if something is capable, we have to have some sort of target on these. Let's say use target value of, we're just going to say of 1 and 1.5 for CPK and CP respectively. So we're being a bit conservative with the CPK threshold there. What else? Provide a brief description of each group. And this is the important piece, and give a representative variable, process variable for each. Also, provide a variable count for each group. That's quite useful. How many? But don't list all the variables. I was coming to the idea now, actually, it might be quite nice if there's a way of it to memorize. If this is a useful prompt, you're probably going to want to use this over and over, so it'd be nice to have a memory. It kind of doesn't fit into a single line like this, but I'm going to copy that just in case anything goes wrong. I've not tried this prompt or anything as complex as this, but I think this is a sensible thing to do for this volume of data. So let's see what we get. It's going to take some time to think about that. Large language models are not very good at arithmetic. So it's going to use a more powerful model in order to be able to do this type of analysis for us. Okay, so we've got capable, not capable, process shift, and other. And let's just see what the other is. Well, the other they've just done is borderline. These processes are adequately centered to pass the CPK threshold, but their overall variation is slightly too wide to meet strict. I like this classification. This is, I would call, not robust. It's the situation where actually CPK is on target, but CP is not. It's a fairly rare event, and a lot of people can't get their head around this one. The other 3 should make sense. Capable, you've got good CP and good CPK. I'd kind of like to give it a nudge and not describe it this way, but just describe things as good or bad. But this CP is good, CPK is good. Here we've got CP is bad and CPK is bad. That's the easy, that's the capable and not capable. The interesting scenarios, I think, are when one is good and the other one is bad. So here, CP is good and CPK is bad. That's the classic case when you've got a process shift. But you can have it the other way. CPK is good and CP is bad. And that's this other one, which is the borderline. So really happy with that 4th classification. I'm glad I put that in. We've got 55 variables that are capable, so that's nice to know. A1 is one example. The not capable, we've got 52 variables, so roughly 50-50 in terms of the split of the data. And an example would be the A to N variable. So let's just get a feel for the numbers here. Yeah, so CP of 0.18 and a CPK of minus 0.05. The process shift, we only have a single variable with a process shift for these targets, the way I've defined the targets, and that's the ply 10. And we've got 10 variables which are borderline. So these ones are just kind of not robust. The CPK is good enough, maybe because, to be honest, we chose a fairly conservative threshold for CPK. But nonetheless, that's good. So, and then we've just kind of got this sort of summary at the bottom. So I think that is really useful. It would be hard to do this just by, you could write some JSL that had rules for the different CP and CPKs to kind of come up with this. But I think that's quite a good classification. Let's just see if there's other things. I think there's something interesting in here. Notice this here, we've got this CPK of minus 0.05. So I was saying a lot of people don't understand this scenario where you've got a good CPK but a bad CP. The other thing that people might not understand is, what does a negative CPK mean? Okay, so CPK can go small but negative. What does it mean? It means a negative CPK indicates that the process mean is outside the specification limit. So it's shifted so far that the mean, not just the tail of the distribution has gone outside the spec limits, but the entire mean has gone past. So again, this actually could have been, we could have maybe had a fifth classification, which is where we've got an extreme process shift. Okay, and again, just to maybe illustrate, I've not really illustrated this, but let's push that down to a single sentence just to give me a more succinct answer to this question. A negative CPK indicates the process mean is outside the spec limits. And it gives you an illustration for this particular variable. Now, what I'll do is use another data set to show you a complex scenario. So these data, I used to sort of teach or do presentations around time series analysis in JMP. I don't think it's a commonly used platform, which is why I want to focus on this, because it's something maybe we do occasionally and we forget some of the details. So let's see if we could do time series analysis on this. We could ask a general question that I know. So I know how to do time series analysis, or at least I've been taught how to do it, but it was 30 years ago when I learned to do it. I happen to have some familiarity with it because I've done presentations on it more recently. And I know we use what's called a Box-Jenkins methodology, but I could ask it, for example, to explain Box-Jenkins. So this is a knowledge type question. Explain the Box-Jenkins method. Oh, and I probably don't want a single sentence for that. Let's just keep the default. So the Box-Jenkins method, it is a systematic methodology for creating ARIMA models. And the key thing with these models is you have an autoregressive component and a moving average component. And one of the key things you have to do is identify whether you've got autoregressive components or moving average components. And you do it by looking at autocorrelation functions and partial autocorrelation functions. Why am I telling you all that? Because, well, I'm going to do time series analysis on Y. When we see the output, and I think for a lot of people, they may have never used the time series platform, but what you get is this sort of histogram here, which are the autocorrelations, or the ACF, the autocorrelation function, and on the right-hand side, the ACF. Now, the way you interpret this is easy to forget, and the only reason I really remember it is because I'm working with simulated data, and my data table tells me this is a second-order autoregressive process. So I know the answer only because of the title of my data. What you look for, if I look at the graph on the right-hand side, after lag 2, the bars reduce. So there's only two significant bars. It's confusing because there's 3 bars, but the first one has got a lag of 0. So we've only got 2 lags. So the time series data, one data point is dependent on the prior data point. And how far back in history do you go? Where we've got order 2 here. So I've got a second order stochastic process, which is either going to be moving average or autoregressive in nature. And the fact that this graph on the left-hand side decays exponentially tells me it's autoregressive. Now, to be honest, it doesn't tell me that. But I know it is. I know one side, either the graph on the left or the right, will be exponential, and the other graph will tell me the number of terms, but I never remember which way round it is. And so I know this is either second order moving average or autoregressive based on what I'm seeing, but I wouldn't remember which way round things are. So what I'd want to do with the large language model is do this. Is it a moving average or is it autoregressive? And if I'm pretty sure it's order 2, but I can ask that question as well. So the time series appears to be autoregressive process of order 2. There you go. That's the answer. So, and then there's an explanation of how it comes to that conclusion. So it's come to the right answer. We could have asked the question in lots of different ways. If I just come back to some of these questions, there's quite a few here, because I think there's an awful lot of information which you're not going to use the time series platform, to be honest, if you don't know anything about time series modeling. But I think for a lot of people that might have a vague memory of having studied it in statistics or maths or economics or something. So here we have these ADF statistics. This is I think it's the augmented Dickey-Fuller statistic. Let's do interpret the ADF results. So yeah, the augmented Dickey-Fuller statistic, and it gives you an explanation of what that statistic is. Let's just do a couple of other of these options, but basically we're going to get to the same point. Well, let's just explain the Bock-Jenkins methodology in relation to these results, and let's try and give me nice formatted output to this. So it's going to be the same answer really as what we saw with the moving average and autoregressive, but probably with more detail. So this identification phase, it's explaining the interpretation of the ADF statistics. And this is one place where normally I would say, large language models are too verbose, there's too much information. This is one place where I would want to see this level of detail. And you'll notice at the very bottom, it says, based on this, it leads to proposing an ARIMA model 200. So it's come up with a full specification of the ARIMA model. So that is really very, very impressive. So this has really finishes what I wanted to talk about in terms of talking about the integration of large language models. And I wanted to get from a point where this was an intellectual curiosity of, can you just physically and technically do this, to the point of, okay, does it go beyond interesting and impressive to actually being useful? And I think this is starting to get to the phase where there is a sort of genuine utility if you can integrate these interpretations based on what you're actually looking at inside JMP. What do you think? Maybe give me some ideas in the comments, maybe ideas as to the type of questions you would ask using the large language model, or just your comments on whether you think this is or isn't useful. Thanks for your time. Bye for now.